Hello, welcome to another module in this massive open online course. Alright. So, in the previous module we have looked at different digital modulation schemes. In this module we will start looking at another digital modulation scheme, that is quadrature phase shift key. Okay. So, let us start looking at, in this module let us start looking at quadrature phase shift key, also abbreviated as QPSK. So, this stands for quadrature phase shift key. So, this, as we have again said several times before, this is another digital modulation scheme. This is another digital modulation scheme. Consider the following basis functions. Okay. So, let us consider again P1t, P2t. These are again unit energy signals. Now, unlike FSK, we have P1t equals square root of 2 over t cosine 2 pi f c t, and P2t equals square root of 2 pi f c 2 over t sine 2 pi f c t, both for 0 less than equal to t less than equal to t, and t equals k over f c, that is the duration spans an integer number of cycles. This we have seen several times before, that is duration equals an integer number of cycles. Okay. So, now if you look at this, okay, remember in frequency shift keying the pulses were cosine 2 pi f1t, cosine 2 pi f2t, they were frequency shifted versions of each other. Now, here we have cosine 2 pi fct, sine 2 pi fct. Now, again once again we have, if you look at this, square root of 2 over t cosine 2 pi f c t, let us say sine 2 pi f c t, f c t plus pi by 2, this is equal to square root of 2 over t cosine 2 pi f c t. So, these two pulses, so cosine 2 pi f c t is obtained by sine 2 pi from sine 2 pi f c t by shifting the phase by pi by 2. So, the two pulses, observe that P1 or P2t is a phase shifted version of P1t. It is a phase shifted version of P1t. I have I am shifting the phase of sine 2 pi f c t by pi by 2, I get cosine 2 pi f c t. So, these two pulses p1 t and p2 t, so p2 t is obtained by from p1 t by phase shifting by pi by 2. Similarly, p1 t can be obtained by p2 t by phase shifting by minus pi by 2. So, the basic point is that these two pulses are phase shifted versions of each other. And once again, you can see both the pulses also have unit energy, alright. We have already seen square root of 2 over t cosine 2 pi f c t, this has unit energy, and in fact if you look at p2 t, that is integral minus infinity to infinity p2 square t dt, that is equal to integral minus infinity to infinity sine square two pi f c t dt. I am sorry, integral from, well, this is from 0 to, this is from we can 0 to t, this is equal to 2 over t integral 0 to t 1 minus cosine sine square theta is 1 minus cosine 2 theta divided by 2 times dt, which is again, if you can look at it, 2 over t into t over 2 minus sine 2 pi f c t divided by minus 1 over t, this is of course again t over 2, 1 over t, this is not 2 pi, apologize, this is 4 pi f c t by 4 pi f c between 0 to capital T, and this part, this is 0. So, this is going to be again t 2 over t into t by 2, this is equal to 1. So, E p. So, what I am trying to show is that energy of both the pulses, that is, if you look at both these pulses, again that goes without the saying from symmetry, energy of both these pulses of both is unity, that is, we have E p equal to 1. Further, if you look at the inner product, now coming to the inner product, we have integral minus infinity to infinity p1 t p2 t dt, which is equal to integral 0 to t 2 over t, well, sine 2 pi f c t into cosine 2 pi f c t into dt equals 1 over t integral 0 to t 2 sine theta cosine theta is sine 2 theta. So, this is sine 4 pi f c t dt, which is equal to, if you integrate this, this is again 1 over t sine 4 pi f c t integral is cosine 4 pi f c t divided by 4 pi f c between the limit 0 to t, and now again of course let me just substitute the limits. This is cosine 4 pi, now f c into t is k, so 4 pi k minus cosine 0 is 1 divided by 4 pi f c, cosine 4 pi k, this is equal to 1. So, this is basically equal to 0. Okay. So, inner product of the two pulses. So, if you look at the inner product between pulse p1 t and p2 t, the inner product is 0. So, both these pulses are basically orthogonal. So, inner product of pulses inner product of pulses is 0, this implies the pulses are orthogonal, therefore P1t. So, square root, if you look at P1t, P2t, square root of 2 over t cosine 2 pi fct, which is your P1t, and P2t, which is square root of 2 over t cosine, or rather sine 2 pi fc of t. These two pulses P1t, P2t, these are both unit norm, unit energy, plus orthogonal, implies they form the orthonormal basis for a signal space, form orthonormal basis of they form the orthonormal basis of a signal space, okay. And this is similar to, if you look at this, this is similar to quadrature amplitude modulation. If you remember, some of you who have done a previous course, this is similar to quadrature, not quadrature amplitude modulation, I am sorry, this is similar to quadrature carrier multiplexing. Well, in quadrature carrier multiplexing, which is an analog modulation scheme, remember quadrature carrier modulation is an analog modulation scheme. In quadrature carrier multiplexing, what we do is we modulate a message signal m1t onto cosine 2 pi fct minus m2t. So, two different message signals can be modulated, one on cosine and one on sine, because these two are orthogonal. So, these two carriers are orthogonal. We have seen in quadrature carrier multiplexing that these two carriers are orthogonal. Therefore, you can modulate two separate signals, message signals m1t comma m2t can be modulated on so one can modulate. So, what we have seen in quadrature carrier multiplexing is we have cosine to consider for a carrier frequency fc, we have cosine 2 pi fct, sine 2 pi fct. We have shown that these two carriers are orthogonal, and therefore one can modulate two separate signals m1t, m2t, one on each carrier, m1t on the cosine channel, m2t on the sine channel. In fact, these are known as the in phase and quadrature channels. Okay, so that is important. This is an analog modulation. Quadrature carrier multiplexing is an analog modulation scheme. Similarly, in digital communication, we have two pulses, cosine 2 pi fct and sine 2 pi fct. Both of these are orthogonal. Okay, both of these are phase shifted versions of each other. Okay, and we can similarly modulate two separate information symbols, digital information symbols on each of these subcarriers. This is nothing but quadrature phase shift key. Okay. So, what I am going to do now is basically I am going to generate my signal xt as a1 times p1t plus a2 times p2t. Now, notice that I am modulating not one symbol but two symbols a1 and a2. So, two symbols or two bits can be modulated on P1T and P2T. Okay. For instance, so and each can carry one bit of information, they can carry more also, but to begin with let us say each carries, to begin with let us say each can carry a single bit of information. For instance, example A1 equals plus or minus A, A2 equals plus or minus A, and for bit energy equals EB, average bit energy equals EB, we have seen already from BPSK. This implies A equals square root of EB, so that one can ensure average bit energy. So, this is plus or minus square root of EB plus or minus square root of EB. Okay. And therefore, now each carries one bit of information, A1 carries one bit of information, A2 carries one bit of, so each carries one bit of information. Implies xt equals A1 P2T plus A2 P2T since A1 and A2 carry one bit of information each, xt in total carries 2 bits of information. X2 carries 2 bits of information, since each A1 and A2 carry 1 bit of information. Okay. So, similar to quadrature carrier multiplexing, separate bits of information. In quadrature carrier multiplexing, it's an analog modulation scheme. So, separate message signals M1T and M2T can be modulated on the orthogonal carriers. Here, we are transmitting separate information symbols A1 and A2 on the two orthogonal pulses, that is cosine 2 pi fct and sine 2 pi fct. These are two orthogonal pulses, unit norm orthogonal pulses. They form the basis, the orthonormal basis of a signal space, which is generated by linear combinations of these pulses. Okay. Now, therefore, the total number of possible signals we have, each A1, A2 can be plus A or minus A. So, the possible set of signals is A1 equals A. So, let us write the possible set of signals. So, this is going to be A times P1T plus A times P2T, A times P1T minus A times, that is A times P2T, when A2 equals minus A times P1T plus A times P2T, and finally naturally minus A times P1T minus A times P2T. This is the set of 4 possible signals in this scheme, set of 4 possible signals. Since each can be plus or minus A, so we have total 4 possible transmit signals xt. We have 4 possible transit signals xt. Okay. And this forms the basis of quadrature phase shift keying. We are going to explore this further. This forms the basis. For QPSK, or basically quadrature phase shift. This forms the basis for quadrature phase shift key. Okay. So, that is what we have. So, what we have seen in this module is we have seen an introduction to a new digital modulation scheme, and in fact a very important digital modulation scheme, which is quadrature phase shift keying. We have not seen such a scheme before, because so far the schemes that we have seen, that is BPSK, binary phase shift keying, amplitude shift keying and frequency shift keying, all carry one bit of information per each duration. Okay. Now, here we are seeing a scheme which is using two pulses which are orthogonal to each other and transmitting independent bits of information on each pulse. So, therefore, we are able to convey 2 bits of information per duration of a single symbol, per a single symbol duration, that is capital T. Okay. So, we have seen the possible, we have seen the basic signals, that is square root of 2 over t cosine 2 pi f c t, square root of 2 over t sine 2 pi f c t. These are both unit energy, orthogonal. And now we are generating a signal by a combination of this. There is A1 P1T plus A2 P2T, that is modulating A1 on P1T, A2 on P2T. Each A1 can be plus or minus A, A2 can be plus or minus A. So, we are able to transmit 2 bits per each symbol. Okay, and we have a possible of 4 possible transmit signals were generated by all possible combinations of A1, A2, and this forms the basis of quadrature phase shift keying. Okay. So, we will stop here and we will continue to explore this in the subsequent module. Thank you very much.